Next we have exercise 9, and in this one we have the distance function dl infinity on the set Rn of all n tuples of real numbers, ordered n tuples, and we came across this in example 9. So now we have to prove that this is a metric space. The solution starts like this. We saw similar solutions before. So we take any 2 points x and y in Rn with these respective coordinates xi's and yi's, and then we recall the definition of this function. Cannot call it metric now itself because that's what we want to show. So let us instead call it distance function. So its definition is this: it is the supremum of absolute values of the corresponding coordinate differences xi minus yi as I varies over this range. Because there are only finitely many elements involved in this set, that is why this supremum actually is just maximum. So next we go for the axioms. If x is not equal to y, obviously some coordinates must be different. There must exist some j in this range such that xj is not equal to yj. Now according to the definition of this dl infinity value of x comma y is the supremum or maximum of all these absolute differences. So because it's the maximum, it is greater than or equal to all of them. In particular, it's greater than or equal to this specific absolute difference which corresponds to the index j. Okay. However, xj and yj are distinct real numbers. So this will be a positive real number. Note that in general this is non-negative, but because it cannot be 0, so it has to be positive. So that is why for distinct points x and y, the distance function gives us positive distance value. So that is one of the conditions. Next, we consider x and y to be the same. Then each xi would be equal to yi, the corresponding yi. And so all the elements of this set are going to be equal to 0. So their supremum obviously is also 0. So in this case, the dl infinity value of x comma y is equal to 0. So another axiom has also been verified. It's true. Next we go for symmetry. Symmetry is equally easy since mod xi minus yi is equal to mod yi minus xi for all I. That is why dl infinity distance of x comma y is equal to the same distance of y comma x. So that's why we also have symmetry. And finally we have triangle inequality. For the triangle inequality, we are going to need another point. So let's that be that point. You know this pattern, okay? This also you saw 2 times before. So then what we do, we consider the dl infinity value of x comma z. By definition, this is the supremum or maximum of the set of all numbers of this form mod xi minus zi. Now the maximum obviously is going to be one of them. So it will ultimately be equal to one such element of that set. Say mod xk minus zk for some k. Okay, no matter what this k ultimately is, it will be one of them. This of course is not the case when you consider supremum or infimum of an infinite set of real numbers. For example, if you consider the set of all reciprocals of positive integers, that set has infimum 0. 0, however, is not an element of the set. But because here we are dealing with finite set, so supremum is maximum, and that is why it will be one of the elements. Alright. So now what do we do with this information? So we again write this. Okay, dl infinity x comma z is equal to this. Now on this we are going to apply the ordinary triangle inequality we have available to us in the system of real numbers. And using that we can write in place of this mod xk minus yk plus mod yk minus zk. So then this is less than or equal to this sum. Now you think of dl infinity value of x comma y. It is the supremum of all real numbers of the form mod xi minus yi. This is one such number. So this dl infinity value may not be equal to this, but because it's the supremum of all such numbers, this is greater than or equal to this. Similarly, what is this dl infinity value of y comma z? By definition is the supremum or maximum of all numbers of the form mod yi minus zi, and this is one such number. So this will be less than or equal to this. So that's how we have our triangle inequality. Distance between x and z is less than or equal to distance between x and y plus distance between y and z. So that's it. We have verified all the four axioms, and so that makes dl infinity a legitimate metric on Rn, and so this pair is the metric space. That's the solution. Next we have exercise 10, and here we have to prove the inequalities in 12(2). So we don't remember this, so these are the inequalities. For any two n-tuples x and y in Rn, 1 divided by square root of n times the L2 distance between x and y is less than or equal to the L infinity distance between them, which is less than or equal to the L2 distance between them. So let's establish these inequalities. We start the solution by writing the coordinates or components of x and y, the usual xi's and yi's. And also let the L infinity distance between x and y be this. Now you know very well, because there also you wrote mod x k minus yk. Here also if you want you can write k, but I have decided to write j. Okay, where j lies in this range. Now we start our calculation by taking the square of this in L infinity distance between x and y. So that will be the square of this. Now if you also include along with this square the other squares, similar squares where you have all the I values, all the way from 1 to n, not just j, then obviously this will be less than or equal to this, because all the terms in this sum are non-negative real numbers. That is why we have this inequality. But what is this? This is almost dl2 value of x comma y, but we do not have the square root. So that means it's the square of the dl2 value. So that's how you have this inequality, that dl infinity x comma y square is less than or equal to dl2 x comma y square. Now you take square root on both sides and you will have this inequality. And you can do this because these distances are non-negative real numbers. That's why you are able to take square root and cancel square root and square freely without any problem. And next we go for this inequality. This time we instead start with the square of this. In the previous calculation we started with the infinity distance and ended with L2 distance. This time it's in the opposite direction. We start with the square of the L2 distance between x and y, which of course you already know is equal to this, okay, this sum. Now what will happen if we replace all the terms of this sum by that fixed mod xj minus yj square? Because that is the maximum of all these terms. all this mod xi minus yi squares. So obviously this sum will be less than or equal to this sum. Now in this sum, although I is varying from 1 to n, and as such there are n terms in this sum, but all the terms are fixed now. This j is fixed. So you can take this j common out. J common out means this entire thing common out. So that will leave you with this sum of n ones. That means this equals n, this thing equals n, and this is, you already know, the square of dl infinity x comma y. So now what are you getting? You are getting the inequality that this square is less than or equal to n times this square. So now there are only two steps. First you take square root on both sides. No problem with having these quantities because they are non-negative and n anyway is positive. And then you divide both sides by square root of n, which also you can do without affecting the direction of the inequality because square root of n is a positive real number, and that will give you the first inequality. So you do this last part yourself and you will get the solution. Next we have the 11th one, and in this one we consider the pair x comma d disk. So it is that thing which we called discrete metric. We saw this in example 11. So we now have to prove that it is also a metric space. Here x is any set. In this solution we straight away in the beginning itself we take 3 points x, y and z. This time however there is nothing special about these points because the set x is general, unlike the previous cases where the points were n-dimensional vectors. So then we recall the definition of d-disk. It's the discrete metric. We are going to show that it's metric, but let's just call it metric. What is its definition? If the points x and y are different, then it is defined to have the value 1. Otherwise, if they are same, then the value is 0. So by that definition itself, d-disk value of x comma y is 1, which is greater than 0 if x and y are different. Otherwise, if x and y are the same, then this is 0. So just from the definition itself, the first two axioms follow immediately. Also, it's trivially true that d-disk is symmetric. Exactly how? Well, you consider these two cases. If x is equal to y, then by definition d-disk of x comma y is 0 and d-disk of y comma x is also 0. So they are equal. Otherwise, if they are different, then d-disk of x comma y is 1 and d-disk of y comma x is also 1. So then also they are equal. So that's how we have symmetry. And finally then we go for triangle inequality. So this is our triangle inequality. D-disk distance between x and z is less than or equal to d-disk distance between x and y plus d-disk distance between y and z. And this inequality can fail, does fail, precisely when these are the cases. These are the cases means when this is the case. When d-disk value of x comma z is 1, but these two other d-disk values are both 0. Obviously, if this is true, then this inequality cannot be true, because on this side we will have 1 and on this side we have 0 plus 0. 1 is not less than or equal to 0 plus 0. But we are saying that precisely in this case this inequality will fail. What are the other cases? Does the inequality hold in other cases? The other cases are this: that you have 0 here, alright, and you have something here. Okay, something here means you can have 0, 1, any combination you can have. because 0 after all is less than or equal to any non-negative real number. So that is why if the left hand side is 0, then the inequality is automatically true. Note that nothing is negative on this side. But if we do have 1 here, then we need at least 1 on the right hand side. Either this is 1, let me actually tell you the cases. This is 1 and this is 0, then also no problem, 1 is less than or equal to 1 plus 0. The other case is this is 1 and this is 0, again no problem. And the only other case is that both of them are 1. Again we have our inequality true. So this is the only problematic case in which this inequality fails. But what do these conditions give us? If x and z must have distance 1 between them, obviously they cannot be equal because otherwise the distance would be 0. So that is why x should be different from z. However, we only have 0 distance from D disk when x and y are equal, when the points are equal. So this being 0 means x is equal to y, and this being 0 means y is equal to z. So in one hand we are getting x to be different from z, and in the other hand we are getting the fact that they have to be same. So these conditions cannot hold actually. In the other cases the inequality is obviously true. So that's how we have our triangle inequality. And as such, D disk is a metric on x is any set, and the pair is a metric space. It's called a discrete metric space. And let's just end the video here itself. There are a few other exercises that we will solve next week. So see you next week with more exercises and their solutions. Until then, this is me, Lucifer from a mathematical room. Have a nice day.